Hi, everybody. My name is Hillel Sreter. I'm an engineer at NeuroBlade. And today I'll be talking about the integration we built with Presto C++ and our accelerator, our data analytics accelerator, which we call our SPU. So first I'll introduce our company. What do we do with our company? We build a data analytics accelerator. It's a hardware. We call it an SPU. This accelerator helps our customers scale their clusters efficiently. This accelerator is built with the data analytics workload in mind, so it's optimized for this type of workload. Okay, so from I guess a software perspective of what you see when trying to integrate this accelerator into Presto or into any query engine really. So what we have is what we call our DAXL. DAXL is our API, our SDK, the SPU's SDK, which is a set of APIs which you'd use for planning, optimizing, and executing your query over the SPU. Okay. So we're building a hardware accelerator. So it's like you're starting down low over here, and we're talking about a Presto cluster, which is way above. So before we even start to build that integration and to test end-to-end over Presto, the first idea is to kind of lay out a premise where the SPU, this accelerator, can accelerate compared to Presto-Velox. So what we did is we built a couple of targeted queries that target very specific data analytics workloads, such as group bys, aggregations, dynamic filters, inner joins, filters and projects, and we compared a Presto-Velox single worker to our SPU. It's actually 4 workers, a single node. What we saw was results which definitely motivated us to move forward into the next step, which we saw between a 5 to 11x performance gain of running over the SPU rather than running on the CPU using Presto-Velox. So the next stage after that was really to build this integration. So we wanted to integrate, enable Velox to utilize the SPU. So we had a couple of guidelines and approaches of how we were going to go through and do this. The first one was we didn't want to mandate any changes in the coordinator for supporting the SPU. So what we did was really a worker-level integration. Worker-level integration means it was all embedded inside Velox. So all the SPU/DAXL logic is inside Velox. The coordinator is unaware. You can add logic and optimize, knowing that a coordinator knows that it has accelerated worker nodes, but it's not a must, and that's what's important. The second important guideline for us was really keeping Velox as clean as possible. Of course, the flows which continue to run on the CPU should be untouched and continue to be as optimized, and Velox should perform as well as it does without the SPU and without this integration involved. And we wanted also the SPU logic flow to be as coherent as possible in Velox's execution. What does that mean? It means that we executed on the SPU, we're reading back results. We want that kind of like a seamless flow from the SPU, which is our data analytics accelerator. We executed there, we're reading the results back to the CPU. We want Velox to continue and execute over the results as seamless and as optimized as it did beforehand. And the last one, which is super important, which is completeness. Completeness meaning you have a worker, or what we call an accelerated worker, a worker running over the SPU. It should be accelerated and not limited in any sort of way, or limited compared to the non-accelerated worker. So we don't want to add any new limitations to it. Basically, the most important aspect over here is a fallback, a seamless fallback, a clean fallback. If the SPU, for example, is busy with a large query queue, then we want to be able to fall back to the CPU and fall back without any overhead or without any penalties, etc. So these were kind of like our guidelines of what we did when we built the integration, which is why we built the integration inside Velox and then connected that to the Presto CPP and then onwards to the whole full cluster. So this is kind of just an example to get a feel and understanding of the evolution of that local plan inside Presto and what we're doing to it. So we have this example of a plan which has two pipelines reading 2 scan tables. They're going through a couple operators, and then they meet at the hash join and continue onwards. The logic we added into Velox's local planner is logic which will iterate over this local plan. It will identify all the operators that can be pushed down into the SPU, into our data analytics accelerator. We'll identify them, we'll push them down, convert them into an SPU program using the Daxel APIs. And then we'll replace all those nodes that have been offloaded and pushed down into SPU into a Daxel scan node. Basically, the Daxel scan operator is in charge of reading those results back from the SPU into the CPU. And so Velox can continue and execute this hash join and aggregate in this specific example. Another important point, just to emphasize again, so the Daxel scan node on the CPU or Velox's side, it's in charge of reading the SPU results, but it hides behind it all those operators which we're offloading now into the SPU. So that's kind of the integration and the guidelines and what we did. And after we completed and built that integration, the next step is to test performance, see how. So we saw those kind of lower level targeted queries. We saw good results over there. Now we want to see the behavior once it's connected into Velox, Presto CPP, end-to-end workload. For this, we tested on TPC-H, a scale factor 1K. We used an 8-worker cluster, 2 server nodes. Each one has an SPU, so the 4 workers are all sharing that same SPU. SPUs can serve the accelerator can serve more than 1 worker, not limited. This spec is kind of like we kind of tried to follow the guidelines of IBM teams benchmarks that they use. And anything else interesting over here? No, continue. Okay, so over here we see 2 pie charts taken from PBench, which is an open source profiling tool built by the IBM team. They helped us out also with setting this up, setting up the Grafana. So thanks to them for that. So what do we see over here? What we see over here is on the left side is the Presto-Velox, and on the right side is the accelerated Presto-Velox. We see operator breakdown. So there are 2 pie charts of the wall times of all the different operators. And one thing that comes to mind that like pops out right away is the table scan. So we could see how that table scan, which is super dominant, I'm not sure if I said, so this is the full TPC-H benchmark, 1K, and this is the wall time of all the operators, kind of like the sum of everything. So what we see over here is that the table scan operator pops out right away. So it's on the right-hand side, it doesn't exist because it has all been offloaded into the SPU. We see the total wall time of this operator was reduced drastically from 13K seconds to 1.7K seconds. Again, I'll just emphasize that Daxel scan operator over there hides behind it. All the other operators were offloading as well. So we see the filter and project. We see some offload over there. So the numbers of filter and project is that delta, the difference between the 4.8 to the 3.8K is the filters and projects that have been pushed down into SPU and running on the SPU. Partial aggregations more or less have been totally pushed down into the SPU. Another interesting thing to point out over here is the exchange operators. We saw as well that the exchange operators wall time dropped as well from 4K seconds to like 2K seconds, 2.8K seconds, which is super interesting because we're not offloading that. So that was interesting for us, and I'll talk about that a bit more to kind of understand how the SPU was able to help reduce those numbers as well. Okay, another aspect is like the offload that the SPU is able to do for the CPU. So on the right-hand side, you see a bar chart, which shows per each TPC-H query how much of that query has been offloaded into the SPU, essentially freeing up the CPU to do other work, with other work either being the operators that we didn't offload, and the CPU can invest more resources into those operators, or be it more queries and get larger throughput for the system. So we saw a pretty good push down. We're working always on supporting more operators and being able to offload more and push more, but we do see about a 50% at most of the queries, if not more. In general, our outlook is not the run it on the SPU and don't run it on the CPU, but rather it's a system that we want it to run together. We want that our data analytics accelerator and the CPU to execute as a full system together and better. And which means that also, of course, the accelerator should do what it's supposed to do, which is accelerate those operations that are pushed down to it. But moreover, it's important that we're freeing up the CPU to do other things. And finally, also the SPU tends to take tends to start off with those scans, read the large, vast amounts of data before we go through all those data reduction operations, such as filters and aggregations, etc. So where the CPU usually even invests a lot of times in processing the large, vast amounts of data, has now been moved to the SPU. So the SPU is processing, reducing the large amounts of data, and then passing back to the CPU to complete it on the filtered out and cleaned out data set. And all this is pretty seamlessly, meaning we integrated into Velox, and then once the Velox integration was complete, it was pretty seamless already. It's the Presto CPP, take that integrated Velox, coordinator hasn't been touched at all, and move forward from there. Okay, so this is another, we found it quite interesting to kind of take a specific query just and to see again that what changed or how the dynamics shifts once we add the SPU into the mix. So we took query 15 specifically to kind of look at that. What we're pushing down in query 15, what we're offloading in query 15 is the table scans and the partial aggregations in query 15. I won't go into the pie charts here just because in the coming up slides it's bigger and then we can actually see what's written over there. So again, this is a view of the operator wall time, but just now specifically for query 15 and not the full TPC-H benchmark. Again, we see how we reduce the dominance of the table scan operator. It's been reduced to percentage-wise, it moved from about 60% to maybe 20% over there. I'm not sure the percentage. But also real wall time, which is more interesting, actually. It's been reduced from 374 seconds down to 6 seconds. And again, that Daxel scan over there is hiding behind it also the partial aggregations, which we could see are pretty dominant as well, right over there, in this specific query. And we're able to reduce that as well, to offload that and reduce the time so that 6.7 seconds is hiding the partial aggregations as well. More so, we also see that those exchange operators that tend to also take a long time, and as we could see on the Daxel side where we added the SPU, they become very dominant. We were able to reduce those run times as well, wall times, as well, quite drastically, which is again interesting because we're not offloading them, we're not pushing down those exchange operators into the accelerator. So that's a super interesting aspect for us to understand how the accelerator is impacting the dynamics, the execution flow of this query to help accelerate those exchange operations as well. So to kind of understand that, what we looked at was the amount of input rows per operator over here. And what we saw was that the exchange operators are, with the SPU involved, are processing much less rows. So their input rows are reduced by about 3 times, something like that, from 453K to about 181K million, rows. And that's so that was super interesting for us to kind of understand what we're doing to help reduce those amount of rows. So as I mentioned beforehand, what we're pushing down into NeuroBlade is the scan nodes and the partial aggregations. And if we look at kind of the breakdown of a partial aggregation, or aggregation, not partial aggregation, if we look at the breakdown of an aggregation operator flow, so you'll have the data source, if that's the previous operation or a table scan. After that, you'll do the partial aggregation. After that, there's the exchange operations for shifting around those, for shuffling around those partial aggregations till you reach the node that will do that final aggregation. In this specific case, The aggregation in Query 15 is done on a key which has a very high NDV. I think it's 100,000 supply key, I think, if I'm not mistaken. So what happens is in the Velox side, so Velox is running over the SPU. The SPU has that hierarchical memory structure, right? So, the CPU, not SPU, sorry. The CPU, so the CPU has that hierarchical memory structure, right? It'll have the L1 cache, L2 cache, L3 cache memory, and you pay a penalty every time you fall through each tier of that memory. So what Velox does to avoid those penalties is that when it notices that it's aggregating over a key that isn't reducing enough, what it does is a sort of an early abandonment of that aggregation, and it will fall back and just let that final aggregation complete the whole thing. With the SPU, our data analytics accelerator, has in it an aggregation engine. It manages its own memory, a large amount of memory in a flat format, highly optimized for data analytics workload, and we handle these types of more difficult aggregations well. So what we're able to do is also reduce that amount of data. But also do it efficiently. So we don't pay that overhead that you'd pay if you're running that same type of aggregation on the CPU. So we're running that, we're reducing the data, which is enabling also just doing that partial aggregation quicker than you would on the CPU, but also doing it more efficiently. So we're helping out those exchange operators later on. So that was a real interesting aspect to see how adding into the mix hardware that's tailor-made and specific for these types of workloads. You kind of avoid all these different corner cases which hurt you when you run on a more general purpose hardware CPU, for example. Yeah, so that was a bit of an overview of the work we've done. A bit kind of looking into how it affects the TPC-H benchmark, and in general what the SPU can do to clusters and the execution flow. We saw a good performance. We saw how we were able to reduce that kind of offload from the CPU. And our next steps, of course, is we're expanding to cloud, which is very important for us, that you'd be able to just grab an instance and run it over the SPU. Today, it's on-prem. We're very soon going to be available on cloud infrastructure as well. We're always working towards increasing more push-down. That's work we're constantly doing to enable more offload, push more into the SPU. And we're enhancing integration model, meaning a couple of different talks today also spoke about it as well. It's complex. Every time you change a benchmark, change environment, you find new corner cases, new issues, new bottlenecks, etc. So we're constantly doing that, and every time we take a step left or right, we find out of new issues which we improve to as well. And of course, we're constantly improving our data analytics accelerator, making it quicker, faster, and to give more benefit. And finally, we have our QR code there. So if anyone wants to talk about it more, myself and Morty is here to talk about it. But also, you could feel free to scan it, sign up, test it, play around with it, and we'd be more than happy to continue talking about that. Thank you very much. If anyone has any questions.
You mentioned cloud coming soon. Do you know what cloud providers or what flavor of cloud?
Yeah, of course, but we can't talk about it now. But yeah, we're working on that, yes. Otherwise, it wouldn't be soon. Yes, I was.
I made like a comparison of C++ with 2 workers versus Java with 20 workers. Have you made any similar, and I know that those comparisons are very specific to the data set and the benchmark you're using, but have you done any similar analysis where you can say 20 node cluster with 32 core machines is equivalent to a 5 node cluster with NeuroBlade?
I understand, yeah. So first of all, we're focused to apples and apples now. So we use that same cluster, and we enable or disable the SPU. So yeah, but that's a type of benchmarking we do now, and yeah. And the numbers and that, of course, we have, and we could share them, but yeah.
So how do you measure how your SPU is performing? Like, what is the metric that you use to test whether your scans are running as fast as possible on the SPU?
So what we measure, so when you do it like kind of like I showed in the beginning, those tailored queries, that's easy because then what you do is you measure the sheer gigabytes per second, right? You know how much data you're bringing in, and you know how long the query took. So that's the gigabytes per second, as simple as that. And we always strive to max out to max out the bandwidth of the system.
One more way of looking at it is in power consumption.
Mm-hmm.
And so do you imagine that that would become a metric going forward?
Oh, it's definitely a metric, yes. The power consumption of our accelerator and how much, yeah. Mm-hmm. We're focused, especially in these benchmarks with connecting to Presto, more with like the latency and throughput measurements, but definitely that's a big part of our measurements as well, yeah.
I mean, I get it from the angle of if at some point we want to rewrite the plan to actually be cost aware in terms of what the SPU is doing,
Mm-hmm.
then we need to kind of have those metrics surface to all of these engines
Yep.
so that they can make better decisions around what to do.
Yeah, I understand, yeah. Mm-hmm. Yeah, I agree. Mm-hmm.
So SPU seems to be hardware optimization, but have you also used it in conjunction with scan optimizations based on sorting or partitioning?
Oh, yeah, definitely. Again, it's integration dependent how you implemented your integration, but specifically over here, the integration we built is such it's a part of the Hive connector. So Hive connector knows how to skip partitions, for example. So the SPU skips those partitions as well. You don't read more than what you would if you weren't using the SPU.
And you also mentioned that a partial aggregation can be skipped and you can move forward to the final aggregation in case it's taking too much memory or something like that.
Yeah, that's a Velox feature. Yeah.
Does that compromise accuracy because that part of partial aggregate may never be computed and it may be computed for the other chunks? And does it affect accuracy, the fact that you skip computing a partial aggregate?
I mean, I don't think so. I don't know. It's the skipping that early early exit of the partial aggregation is a Velox feature. It's not an SPU feature. It's something like commonly used when you see that. So it shouldn't affect, right? I mean, especially not in. I mean, maybe in rounding numbers it can affect. Yeah. All right. Thanks a lot.